Now that we've seen a lot of data structures, we are also going to talk a bit about how long it takes to access them and how long it takes to change something in these data structures. Now, the complexity is usually transcribed and done using the big O notation, like big O of n. Big O notation comes from the mathematics. We're not going to detail too much the math here. I'm just going to give you a feel for what it means, but the math is actually detailed inside your workshop sheet. Now, big O of n or big O of something is actually used to describe the rate of change of how long it's going to take to access a data structure depending on the size of the data structure. So let's take an example. Let's take an array which is really long. It has n elements. So it goes from 0, 1, blah, 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 to n minus 1 and n. Now this array has n elements. How long is it going to take to access an I element in between here? How long is it going to take to access this I element? And maybe this rate of access time is going to change with the size of the array, but it's actually not, because if you remember, if you want to access the I element, we know its index, it's I. So we know the first, the address of the first element of the array is going to be, let's call this array A. So it's going to be the address of A plus the size of the element we have inside this array. So if it's an integer, it's going to be 4 times the index of what we want to access, so I. And this is only the formula to find where the I element is in the array. And it's going to take no time to compute. And you can see there isn't n anywhere inside this formula. So it's going to be independent of the array size, the access time. So the access time is a constant, so we note that big O of 1. It's constant. And same goes for the modification of the array. Now let's take a linked list, for example. I have a linked list. Now inside this linked list I have 1, 2, 3, 4, and I go from one to the other. How long is it going to take, for example, to go at the index number 3 of the linked list? Let's say L, which points here. Well, it's going to take 1, 2, 3, and 4, etc. So to go at the index number I is going to take a long time. And the mean of that, if you have a linked list which is quite longer than that, and goes on and on and on and on and on until we get to index number n minus 1 and n, and then nothing. The mean access time, if you want to access something inside the linked list, is going to depend on the size of the linked list, because we have to jump from one element to the other. So it's going to depend on how long the linked list actually is. And so we say the access time of the linked list is linear compared to the size of the linked list. And if it's linear, we say it's big O of n being the size of the linked list. Now usually, when you have big O of 1 or big O of n, you're actually it's pretty cool. But you can find some much more daunting complexity. For example, if you have a for loop in your Python code and you are doing some processing on X variable, and inside this for loop, for example, you do a process, so let's say a process of X, you are going to loop over some data structure. Let's say we have a list of A, so this whole process is going to be a big O of the size of the A list. So we can say big O of length of A, or let's say big O of, let's say the length of A just n, so it's going to be only big O of n. But what happens now if you do like for x in A, and then you actually want to do for x in A again. So you actually want to do a loop inside of a loop, and you're going to loop over the complete list of A, and then loop over the complete list of A again each time. And then you want to do some processing here. Processing of X. Now what would happen? This actual program would have a complexity of not O of n, but it would have a complexity of n squared. So it's not going to rise linearly, it's going to rise exponentially. So it's not going to rise like a linear function, it's going to rise exponentially. So you have to be really careful about how you write your for loops in your programs, and always check the complexity before you actually spend too much time on a program.